We physicists have held up for 100 years, starting around 1916, for this photo. Is there a local dark opening? It might be among the most enticing and peculiar phenomena of the universe that baffle us. They are enormous monsters in terms of gravity, but simultaneously, for all intents and purposes, imperceptible to us. A dark opening possibly weighs 2 to 4 million times the mass of the Sun. However, based on the research that has been conducted over the last 2 or 3 decades, we've gone from knowing absolutely nothing about them to discovering more and more, up close and personal. And things have recently gotten even more insane. Michio Kaku recently reported that we finally got a glance at what's inside a dark opening, and this new data sheds light on nuances the scientific community may have missed from the start. Join us as we dig further into dark openings and uncover what's inside. Space is vast and mysterious. But what are dark openings? Before we delve into the details of what Michio Kaku found, we have to discuss the basics. Although most of us have some idea of what dark openings are, there are still a few misconceptions. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of dark openings. At that time, the concept of dark openings was purely hypothetical. It took the scientific community an additional 50 years to find evidence that dark openings truly exist. This took place in the 1960s when they were studying the Cygnus X1 celestial body and observed a strangely glowing blue star emitting X-rays. This star was certainly not an ordinary object, it was orbiting an enormous, invisible mass. Further examination revealed that the X-rays were not just moving on their own, they were being pulled into the dark object they were orbiting. Hence, the term dark opening. This discovery was monumental because it provided evidence that dark openings do exist. They were no longer just a product of Einstein's wild imagination. While that was incredible, it also meant there was a mysterious and powerful entity in space that we urgently needed to understand. Scientists from all over the world began investigating. This dark opening was named Cygnus X1. It is a member of a star group approximately 6,000 light-years from Earth. This was no small discovery. Cygnus X1 is multiple times brighter than the Sun and incredibly dense, giving it a strong gravitational pull. This gravitational pull is so powerful that not even light can escape it, which is why it is called a dark opening. The concept of a dark opening is both intriguing and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a dark opening is pulled in and lost forever. This element of danger makes it even more important to understand everything about them. Was this the end of the discoveries, or were we just getting started? The answer turned out to be the latter. After the discovery of Cygnus X1, researchers began searching for other dark openings. They found that there could be nearly 100 million dark openings in the Milky Way alone. However, because they are incredibly difficult to detect, we still don't have an accurate count. By all accounts, there are several million dark openings in the Milky Way, a galaxy in our own cosmic backyard. This makes studying them even more crucial. Breaking down the science. The primary concern with dark openings always revolves around gravity. Their gravitational pull is so intense that anything entering them is compressed into an infinitely small point, a singularity. In simpler terms, dark openings are like massive vacuum cleaners that consume everything in their vicinity. One of the most startling aspects of dark opening research is the idea that if someone were to fall into one, they would reach a point where they are stretched into a single line. This process, known as spaghettification, would take time, but the individual would die before reaching the final stage. So, let's just say that nobody should ever enter one. But since dark openings are everywhere, could we be in danger? Despite the fact that the nearest dark opening to Earth is around 500 light-years away, it's still close enough to raise concerns. In 2021, researchers produced the first clear image of a dark opening in the M87 galaxy. This image was captured over several nights, and with each photo, scientists gathered more evidence. By aligning the individual images, they were able to fill in the gaps and determine that dark openings have 3 distinct layers. Many people assume a dark opening is simply an expanding void, but it is far more complex than that. To even reach the nothingness part of a dark opening, one must pass through the first 2 layers. 1. The event horizon, the point of no return. Once you approach the event horizon, your only option is to continue falling inward, as the gravitational pull is too strong to escape. 2. The photon sphere, a region where light orbits the dark opening. Any light entering this zone becomes trapped and cannot escape due to the immense gravitational force. 3. The singularity, the core of the dark opening, where everything that falls in is compressed infinitely. At this point, the laws of physics as we know them break down, making it impossible to predict what happens inside. What makes dark openings even more perplexing is that each one is unique. Although they follow the same three-layer structure, their behavior and properties can vary drastically. The challenge of studying dark openings. If dark openings were any other celestial phenomenon, we could simply observe them through telescopes and study them in detail. However, dark openings cannot be directly studied. Researchers rely on indirect observations, such as analyzing the radiation they emit and the gas and dust surrounding them. Sending a probe into a dark opening is not feasible. Anything crossing the event horizon is pulled toward the singularity and compressed into an infinitesimally small point. This means that any probe sent in would vanish into oblivion, making it an impractical and costly experiment. Because of these challenges, researchers are left with no choice but to study dark openings in a two-dimensional manner, even though they are three-dimensional singularities. This complicates matters further, especially since the laws of physics cease to function normally inside dark openings. Traditional scientific methods do not fully apply in these cases. How are dark openings formed? One of the most captivating theories about dark openings is that they originate from collapsed stars. When a massive star exhausts its fuel, it can no longer generate enough energy to counteract its own gravitational pull. As a result, the star collapses in on itself, becoming denser and denser. If the star is massive enough, this collapse continues until it forms a singularity. To better understand dark openings, NASA researchers focused their studies on the center of the M87 galaxy. Astronomers observed an immensely powerful whirlpool of superheated hydrogen gas rotating at an astonishing speed of 1.2 million miles per hour. This rapid rotation suggested an incredibly strong gravitational influence at the heart of the M87 dark opening. The observations confirmed that dark openings are not just empty voids but dynamic entities, constantly interacting with their surroundings. One of the most remarkable aspects of dark openings is their ability to warp spacetime. According to Einstein's theory of general relativity, massive objects like dark openings create deep curves in the fabric of spacetime. This means that anything passing too close, including light, gets caught in its gravitational pull, making escape impossible. The role of accretion disks. Surrounding many dark openings is an accretion disk, a swirling ring of gas, dust, and debris heated to extreme temperatures as it spirals inward. These disks can emit enormous amounts of energy, sometimes outshining entire galaxies. The M87 dark opening, for example, has a glowing accretion disk, which helped astronomers capture the first-ever image of a dark opening silhouette in 2019 using the Event Horizon Telescope, EHT. This discovery revolutionized our understanding of dark openings and provided visual proof of their existence. It also allowed scientists to test Einstein's equations under extreme conditions, confirming that his predictions about gravity hold true even in the most extreme environments. Could dark openings be portals? While dark openings are often viewed as destructive forces, some theories suggest they could serve as gateways to other parts of the universe, or even different dimensions. The concept of wormholes, a speculative solution in Einstein's field equations, proposes that two distant points in spacetime could be connected through a tunnel-like passage. If dark openings were indeed wormholes, it might be possible to travel vast cosmic distances in an instant. However, no direct evidence supports this idea, and most physicists believe that any attempt to enter a dark opening would result in instant destruction due to immense tidal forces. Supermassive dark openings and galaxy formation. Most large galaxies, including the Milky Way, contain supermassive dark openings at their cores. Our galaxy's central dark opening, known as Sagittarius A*, is estimated to be about 4 million times the mass of the Sun. Scientists believe these cosmic giants play a crucial role in galaxy formation, influencing the movement of stars and shaping the structure of entire galaxies. Dark openings can also trigger powerful jets of energy, expelling matter at nearly the speed of light. These jets can extend for thousands of light-years, impacting star formation and altering the interstellar environment. The immense energy output of these phenomena suggests that dark openings are not just cosmic destroyers but also fundamental to the evolution of the universe. The future of dark opening research. As technology advances, our ability to study dark openings will improve dramatically. The James Webb Space Telescope, JWST, along with future observatories, will allow us to peer deeper into space and gather even more detailed data on these mysterious entities. Scientists hope to answer some of the biggest remaining questions. What exactly happens inside a singularity? Are dark openings truly singular points, or do unknown quantum effects come into play? Could new physics emerge from the study of dark openings, leading to breakthroughs in our understanding of space, time, and gravity? The more we learn about dark openings, the closer we get to unlocking the most profound mysteries of the cosmos. While they may seem like cosmic enigmas, they hold the potential to reshape our fundamental knowledge of the universe. One thing is certain, our journey to understand dark openings is far from over. Each discovery brings new questions, and as we push the boundaries of science, we may one day uncover the true nature of these fascinating and terrifying celestial objects. The rotating gas disk should have caused it to violently break apart in all directions. However, it didn't. Researchers discovered that there must be a titanic mass concentrated in the galaxy's center to prevent this from happening. This massive object, weighing between 2 and 3 billion suns, had to be a dark opening. But that's not the only theory concerning dark openings. In 1963, New Zealand mathematician Roy Kerr utilized Einstein's gravity equations to provide the best description of a rotating dark opening. He showed that a rotating dark opening wouldn't collapse into a point, as previously thought, but rather into a thin ring or a fiery disk. The disk would rotate so quickly that outward forces would prevent it from collapsing. This rotating disk of matter is known as the ergosphere, the region surrounding the dark opening where the laws of physics begin to break down. However, the most intriguing aspect of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also referred to as a wormhole. This is a theoretical tunnel through space-time that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a dark opening, instead of being crushed into oblivion, they would be sucked down a tunnel through the ring of fire and shot out of a white opening into a parallel universe. To comprehend how this works, we need to look at the concept of space-time in Einstein's theory. The reality we experience isn't composed of independent entities but is interconnected, forming a fabric with 4 dimensions known as space-time. Objects with mass warp this fabric, creating a gravitational field that causes other objects to move toward them. Now, imagine a sheet of paper representing space-time. If you place 2 points on the paper and draw a line between them, this represents how objects move through space-time. But what if you could fold the paper in half and create a shortcut between those 2 points? This is the concept behind wormholes. The idea is that dark openings may serve as gateways to another universe, just like a wormhole. Dark openings hold both great power and deep mysteries, making them endlessly fascinating subjects of study. Their gravitational pull can consume entire stars, yet at the same time, they are also potential windows into parallel universes. The more we learn about dark openings, the more we uncover about the fabric of space-time and the fundamental laws of nature. So, while we may not have all the answers, one thing is certain. Dark openings will remain one of the most profound and mysterious phenomena in the universe for many years to come. As we investigate further into the enigma of black holes, new discoveries and theories continue to challenge our understanding of the universe. One of the most fascinating aspects of black holes is the way they warp space and time. According to Einstein's general theory of relativity, mass and energy bend the fabric of spacetime, and this effect becomes more extreme near a black hole. The intense warping of spacetime in the vicinity of a black hole allows for bizarre and seemingly impossible phenomena. For example, the closer you get to a black hole, the more time itself slows down. This is a consequence of spacetime's warping, known as time dilation. In practical terms, this means that if you were near a black hole, time would pass much more slowly for you compared to someone far away. If you were to fall into a black hole, an observer watching from a distance would see you slow down and eventually freeze at the event horizon. However, you would never quite cross it from their perspective. From your own perspective, time would continue normally, and you would keep falling toward the point of no return, where the laws of physics as we know them break down. This brings us to one of the most baffling questions. What happens inside a black hole? It is impossible to send probes or astronauts into a black hole to answer this question directly, so physicists have proposed several theories. One possibility is that the singularity at the center of a black hole is a point where the fabric of spacetime itself breaks apart and the standard laws of physics no longer apply. The extreme gravitational forces would cause any object to be crushed to an infinitely small point, a singularity. But what happens after this point is a mystery, as our current physics theories cannot explain the behavior of matter and energy in such an extreme environment. One interesting idea comes from quantum mechanics, the branch of physics that governs the behavior of very small particles. Quantum mechanics suggests that spacetime might not be a smooth, continuous fabric but could instead be quantized on the smallest scales, meaning it might be composed of individual components. This concept, known as quantum gravity, could offer a new framework for understanding black holes and the singularity at their centers. Some researchers even speculate that this framework might explain why black holes don't violate the laws of physics. Perhaps they don't actually have a true singularity after all. Another intriguing idea is the concept of the information paradox. In quantum mechanics, information about the state of a particle is supposed to be preserved. However, when matter falls into a black hole, it seems that the information about that matter is lost, violating a fundamental principle of quantum theory. This paradox has led to much debate and speculation in the scientific community. Some researchers propose that the information is somehow encoded on the event horizon in what's called the holographic principle. This means that everything that falls into a black hole isn't truly lost. Instead, the information is stored on the surface of the black hole and might eventually be released in some form. As we continue to explore the mysteries of black holes, one crucial aspect to keep in mind is the discovery of supermassive black holes at the centers of most galaxies, including our own. These black holes can be billions of times the mass of the Sun and exert a profound influence on their host galaxies. Recent observations of black holes, such as those in the centers of galaxies like the famous M87 black hole, have provided new insights into how these cosmic giants shape their environments. In 2019, the M87 black hole was depicted by the Event Horizon Telescope (EHT) collaboration, marking a significant milestone in black hole research. The groundbreaking image of the M87 black hole provided the first direct visual evidence of an event horizon, the boundary beyond which nothing, not even light, can escape. This achievement confirmed long-standing theoretical predictions and allowed scientists to test Einstein's general theory of relativity under extreme conditions. But black holes are not just isolated cosmic monsters, they play a crucial role in the evolution of galaxies. Supermassive black holes at the centers of galaxies influence star formation, regulate the flow of interstellar gas, and can even trigger massive energetic outbursts known as quasars. These quasars, powered by material falling into black holes, can be among the brightest objects in the universe, shining across vast cosmic distances. Yet, one of the biggest questions remains: how do these enormous black holes form? While we understand that stellar mass black holes arise from the collapse of massive stars, the origins of supermassive black holes remain mysterious. Some theories suggest they grew from the merger of smaller black holes over billions of years, while others propose that they formed directly from collapsing gas clouds in the early universe. The study of black holes is also deeply connected to the search for a unified theory of physics. General relativity and quantum mechanics, two of the most successful theories in physics, provide conflicting descriptions of what happens inside a black hole. Physicists are actively working on theories of quantum gravity, such as string theory and loop quantum gravity, to bridge this gap and provide a more complete picture of black holes and the nature of spacetime itself. As our technology advances, new observations will continue to refine our understanding. Future telescopes, such as the next-generation Event Horizon Telescope and space-based gravitational wave detectors, will allow us to study black holes in even greater detail. These advancements could uncover new insights into how black holes merge, how they influence their surroundings, and whether exotic phenomena like wormholes truly exist. Black holes remain one of the greatest frontiers of modern physics. They challenge our understanding of the universe, push the boundaries of scientific exploration, and may ultimately provide answers to some of the deepest questions about the nature of reality. With each discovery, we come closer to unraveling the enigma of these cosmic giants, but they continue to hold secrets that may redefine our understanding of space, time, and the fundamental forces of nature.